present our newest product used for like a semi. We use the semi-transparent pigment to replace aluminum. The title should be same, but I run out of space.
Can you hear me? Much better. Yeah, so with that, we're going to start. I do know how to spray the paint, by the way. So here's the agenda, what we're going to talk about. We're going to give an overview of the effect pigment using automotive coatings and what's important color of the silver play in automotive and how the silver color plays in the autonomous driving world. We're going to introduce a new product which is designed for radar coatings, and we have an example using a running color to replace aluminum with this new product, and how it affects the lightness of the color travel as well as the radar permittivity. And then finally, we have a couple of styling ideas. Use this product with and without aluminum to get a radar compliance. So with that, let's get started. First, we have an overview of effect pigments using automotive colors. So here's our classic slide for Merck, for EMD to give a training, the difference between those pigments. We have absorption pigment, pearl effect pigment, and also metal effect pigments. So for absorption pigment, it scatters the light when the light hit the particles. Normally they're spheres, so the light scatter, that's how you see the color. The color is really not depend on the angle. So with any view angle, you see the color. For example, it's a red or blue. They're going to be red or blue. For our pigment, it's very angle dependent because they're semi-transparent. Part of the light hit the flake and reflect, and the part of them go through the flake, then reflect. So the color you see actually is the interference color. Without light, you don't see any color. So our pigment definitely need the light to see the colors. And finally, the metal effect pigment, which is your aluminum, basically used for the silver colors, they are opaque. The light hit the flake, then they reflect. So you will see this high travel from very bright to dark. So that's the difference between those three types of the pigment using automotive coatings. 90%, 99%. So there are some natural pearl pigments you see in your daily life, like the typical is fish scalp, that's a natural pearl, and also the mother pearl, they're also natural. And this, the right bottom corner, that's actually is a stack of protein. They're pearlescent as well. Man-made pearl pigments, those are the pigments used in automotive coatings. So the natural one we don't use that for automotive coatings. They're super expensive. But those man-made, it varies from a metal oxide coated substrate all the way to aluminum or metal oxide coated aluminum flake. So there are various technology to make those man-made pearl pigments. This is the structure of the typical man-made effect pigments. So they normally are irregular in shapes. Particle size is often reported as an average value. We always report the size distribution, so you know the particle size range. And mica, there's a thickness of the pigment. Mica is about 300 nanometer. The metal oxide layer is somewhere between 50 to 300, depends on the color. the thinner layer is your pearl color. When we increase the thickness of the metal oxide, is your green. The thickest one is your green. Those are the titanium dioxide coated mica. Of course, you can vary the substrate. It could go from mica to glass to aluminum flake. It depends what kind of effect you're designing for. Finally, we do put a surface treatment just for better durability. So this one shows the transparency go that way, and the absorbing is this way, and the reflecting is that way. So you can see which type of pearl pigment or effect pigment positioning. At the corner, that's your aluminum. It's highly reflective and less transparent. If we go up all the way, that would be your glass flake pearl pigments. I know glass flake is used in automotive, start to be used. They're highly transparent, but they're much less hiding. There's almost no hiding. So anything else is set in between. Depends what you want. So you can see if it's a iron oxide coated substrate, it will have a better hiding than titanium dioxide coated, because iron oxide has absorption color, it's reddish color. So your red, your orange is always have a better hiding than your interference blue or your interference green. So that's just how it plays. Here is the summary of the substrate versus the effect you're looking for. We do play the substrate to give you different appearance. Everything is metal oxide coated substrate. So they are either titanium dioxide coated or they are iron oxide coated. But your effect can get with different substrate. So for example, if it's a aluminum, that will give you luminous, so it's much more brighter. And if it's the aluminum oxide, they will have a very high chroma and give you the crystal effect. We move on, silica oxide can give you a multicolor effect because the silica oxide itself play as part of the color. So you will see the color from titanium dioxide or iron oxide coating as well as the silica flake by itself. Of course, the mica in 70 years playing automotive industry, so it's our traditional product. And finally, the borosilicate, that's the glass flake, give you highly transparent. So with that, let's move to the color popularity. So thanks for our marketing group provide this pie chart. So you can see the award and the North American color popularity for Americans. White is the most popular color. I have a white car. I like my white car. I like my tri-coat white car. And followed by black, and then the next would be the silver and the gray. We lump together. It's about 30% color popularity. We're going to focus on this color space to show you how to use this new product to give you the hiding as well as the brightness. So here's the color story I already talked about. It's 20% gray and 9.85% silver. So we lump them together as a gray/silver. A lot of designer like the color. The consumer, of course, like the color, and it shows high sophisticated color. So that's the color popularity. So now we talk about silver color in autonomous driving world. So this slide is provided by my colleague in Merck, Germany. So he's expert than me. I'm just going to present his slide. So here is the shows the sort of the timeline in the left side, where this assistant driving device is going to be used. So now it's like a feet off and the move to hands off, the eyes off, and the minds off. Looks like to 2044 is going to be completely autonomous driving. Am I right? Or is this curve right? Anyway, so there's a lot of a high autonomy level will need a higher assistant level. And there's a lot of detectors surround the cars. So there's more regulation, and supposedly there's up to 40 sensors around the car and 7 to 10 radar sensors. So this talk is more focused on radar sensor permittivity. Here's the detector. Normally it's on the corner of the bumper. Then you have your bumper material, and then you have your coating. Then you have the object to be detected. So the radar ray is supposed to go through all those layers to get to the object and then respond back. So this coating, the white one, it needs some sort of transparency to be able for this radar line go through. For aluminum flakes, since they are opaque, we talk about at the beginning, if you have the hiding and your flake is lying next to each other, so they will block the radar signal. So that's the idea. But we already talked about a silver color is very popular color. We play this triangle. They have a highest brightness on the top, and the hiding power on my left is your right, and the flap. So people like those high travel. They like this from bright to a dark travel. It's always a challenge to style a silver color without aluminum. You lose your high travel somewhat, and then you also lose your brightness at your last angle, your specular angle. That's the light hit this flake and then reflect right at your eyes. That's the highest L value. Then when you're standing on the side of the car, that's your diffuse angle. So this is just saying, if you have all the aluminum flake, in order to get the hiding, line each other, you have a very less chance for radar ray to go through your coatings. So with that, we're introducing our new product designed for radar coating. We call it RDR silver. It's a blue silver. So this is, there's a little car I want to show you to run through. That's a little silver car. Our marketing people did a great job for that. So it's metal oxide coated mica. And this is the electronic microscope look like. That's the product look like. And we have both bright field and the dark field optical microscope. Those are the pigment look like. So they are non-plot metallic, but will give you somewhat metallic look. It also is a bright bluish silver. So it's in our bright blue silver colors family. And it gives you the radar capability because they have a nice hiding power. So you can replace part of your aluminum with this without losing too much L value and keep your hiding. So with that, I'm not going to read every line, but basically it's a blue silver pigment with a fine particle size distribution. Particle size is 5 to 25 micron. Give you very fine, like a satin type of finish. When you use with aluminum, will keep your brightness and remain the hiding power, as well as give you the radar transparency. That's the whole idea about this. And one thing I want to mention is very sustainable product. It's based on the natural bycast, so it doesn't use as much energy as synthetic mud. So that's part of our sustainability campaign. This is based on natural mud. It is also a patented technology. The drying process is fluorinated doped process. I don't know the detail because I'm not in the R&D, but it's patented technology. With that, let's take a look at our family. So we have the blue silver, gray silver family with 2 normal particle size product and a 2 small particle size product. You can see 9602 and the 9612, they're in pairs. They are gray silver. And 9605 and the 9627, they are the blue silver. They are like the 05, 02, they're 5 to 40 particle size range. And the 9612 is less than 15 micron. And 9627 is 5 to 25 micron. So that's what the pigment mass tone by itself look like. And we have some benefit. So the hiding wise, 9627 have a much better hiding than 9605 if you are in the blue silver color space. If you are in the true gray, like a red shade gray side, 9612 has the best hiding power. So with that, here's the comparison of those 4 products. The L value, you can see the bigger particle size, they reflect most of the light. So you will see the higher L value. So they are much more close to aluminum look. They have a higher L value. When you goes down, that's your travel. You can see they have a sharper travel pattern than the small particle size. That's just the product, the nature by itself. And the color travel, this is A versus B. You can see the gray silver, they all in the red yellow side. So those 4 lines, I don't have a pointer, but those 4 lines all in the red and the yellow side. The 9627 and 9605, they're in the blue side. So those 2 lines are in the blue side. And for the light blue one is the 9627. You can see a very little change color. So when you put in the silver color, it doesn't affect your silver as much. It don't shift all the way to the blue like 9605. That's one of the benefit of the product. So here is the comparison of the hiding. For pearlescent pigment, it's very different from absorption pigment. If you guys are familiar with absorption pigment, the smaller particle size is more transparency. So pearlescent is the other way. The big particle size product has less hiding. The small particle size provide a better hiding due to the light scattering. So the smaller one is more close to the spheres, so they scatter much better, much more light than the big ones. So keep in mind, you will see a better hiding power from smaller particle size product than the big particle size product. So we have this chart is showing the particle size and the thickness we do the hiding wedge of the product mass tone by itself at pigment binder ratio 5, like 25 to 100. So this is our standard mass tone formulation. You can see 9627 is about 1.2 mils heights, complete heights. And the 9612 is less than 1 mil. And if you move to the bigger particle size, there's going to be over like 1.5 mils. And those 3, this bar chart is to measure the hiding with different ways, the delta E over black over white. So the smaller delta E means better hiding. So that's where our German colleague like to use this. So we put both there to give you an idea. You can still see, the bigger particle size product has less. And some of the gray bars are the product on the market. similar purpose for radar applications. You can see is the smaller particle size definitely hides better. So flap index, that's one of the attributes of the silver color aluminum, provided they have a very sharp from bright to dark color travel. The high travel means you have a high flap index. So the flap index also depends on the particle size. Normally, if it's the same technology, the bigger particle size will have a better travel. So we'll have a higher number of the flap index. This just shows you the comparison of all those products where the flap index fall. You can see the bigger particle size, definitely it travels more, and the smaller particle size travels less. That's just the way it is. So with that, that's basically pigment by itself, what is provide, what's the benefit of using the pigment. Now we talk about the performance. We do extensive testing for the pigment before we launch to the market. We do the humidity resistance. We also do the weathermeter. We do the flow radar as well. So here is another car goes by. So we have two sets of data to show the humidity resistance. One is the traditional delta E, the DOI from Dorgan, and the dark blue bar is the initial, then it was, you take it right after the humidity chamber, and 1, 4, and 24 hours. So you can see after 24 hours, actually after 4 hours, it's completely recovered. This is 240 hours humidity at 100% humidity, 40 degrees C testing. And on the right side is dullness of the DOI. That's another way to measure the orange peel of your coatings. The higher number means the worse. So you can see it's just when you first take it out, it went up a little bit, but it's recovered after 1 hour. So it was, the product itself have a very good humidity resistance thanks for our surface treatment. This is 4,000 hour weathermeter testing data. We do the mass tone is on the right, on the left. The black letdown is on the right. So you can see the delta L, A, B, and the delta E. So the purple number is delta E. The most of the color change is at your 15-degree view angle. So that's your flash angle. The diffuse angle really don't have too much change. Nevertheless, the delta E after 4,000 hours exposure is well below 2. It's only a little bit over than 1. So that's the performance of the product. Now we're showing a leather study we did. We pick like a silver gray color, which is still a running color. We did a leather study to replace the aluminum with our 9627. Before I go on leather study, this just shows you pigment by itself, how it's performed from the brightness to flap index to the delta E and the radar. The important is the radar reading, right? So you can see your travel from your 15 degrees, your L value is like 90, 99. And when you flop down, it's going to be like 99 to 30 to 39. So that's your travel. And the next is the flap, is have a decent flap index. So that means give you a decent travel. And the delta E, it have a decent hiding. And the radar is well below 30. So this is according to our radar expert. Below 30 is kind of a guideline, but below 10 is definitely good to go. anywhere between 10 and 30 is kind of iffy, depends on the film build, depends on the pigment loading. So you definitely need the lower is better. And here's what we did. We picked the running color. The color has, aluminum flake and some carbon black, some red, some yellow, and a little bit of gold pearl. It's just for highlights, I want to say. And we replaced the aluminum flake with a 9627, and we checked the color, the texture, the hiding, and the flap. So those are the testing we did. Of course, the radar permittivity, that's another parameter we checked. So here's the panel. This is the panel you look at 45 degrees. Like you put the panel right here, you look at. The control is 100% aluminum. Then we replace the, like with 9627, 15, 25, 50, 75, 100. This is what the panel look like. So you can see from like the face, you replace it all the way to 75, you start to see the dark because there's some carbon black in the color. And if you replace a 100% of aluminum with 9627, it's way too dark. So it definitely needs some additional formulation work. But if you look somewhere between 50 and 75, it seems a good place to fit in. We'll show some data. So here's the data. This shows you the almost like the 25, 15 degree view angle. That's your flash color. The one we just showed is your face color, right? So it's the same idea. Somewhere between 50 and 75 replacement, you still have a decent color as a silver color. And if you replace 100%, that's just way too dark. So that's the appearance. Now we take a look of the data. So we did the same thing. This has a hiding at 12 microns. Like no matter how much we replace aluminum, they still have a hiding. So all the data was measured at 12 micron space code. So control, you can see it's very bright. It's 120, the L value at the 15 degree view angle. It dropped down to 30. So you have a very high travel. And you can tell from the flap index and but your radar permittivity is just no way. Look how high the blue bar is. The radar rate will never go through this coating. When you replace the aluminum, you can see the L value start to drop, drop every like a 4 unit. Like you replace from like 15% to 25%, it drop another 2 units. So basically your flap stays same, but your face sort of drop a little bit. And but you can see the radar permittivity is much better improved. When you replace like 75%, is way below 20. So looks like it's somewhere you can replace aluminum from somewhere between 50 and 75. Right? If you use just the pearl pigment, you're there. You don't have to do anything. So that's the data. And here is the color data. We already talked about it. But I want just to show one more thing. You can see actually the LAB, they're quite in the same trend. They're just different a little bit, unless you 100% replace with the 9627. Here's your texture. That's your sparkle. It also stay in some sort of same. Actually, you replace some of aluminum with the 9627. Your sparkle and sparkle intensity stay quite same. So with that, we have some ideas to use this with and without aluminum. So this particular pigmentation is used without aluminum. You can see the L value is very high. It's almost same as aluminum, and you have a decent hiding. The delta E is less than 1, and your radar permittivity is quite well. In this case, we used our ceramic, crystal silver, in combination with our small particle size synthetic mica to give you the brightness. The brightness mainly is coming from ceramic. They're very bright. And if you want to see what actually panel look, please stop by our booth. We have the panel. And this one is with 3% of aluminum. Again, it'll have a decent radar data, but your brightness sort of trying to stay same. With that, I think that's all. That's my summary. So summary, basically, silver is always popular color in the automotive world. It's always a challenge to balance radar permittivity versus the hiding versus the brightness. And 9627 with a small particle size can also give you a decent sparkle as well as the hiding. So that's a good product to be used to replace partial of aluminum or complete replace of aluminum. And we're hoping this product open a lot of opportunities, give you possibilities to style a silver color in the autonomous driving world. With that, see the color me, and that's it.
Thank you very much, Wei, for a wonderful second talk.
Thank you.
If you'd be so kind, we have a few questions, so keep on putting them into the Wova app. The first one, this iridium grade, are you also working on a smaller particle size, that like 5 to 10 microns for two-tone or graphic applications that could be jetted rather than sprayed?
It's always a challenge to jet print the thing out. So to my knowledge, not for jet printing purpose, the smaller particle size is difficult to control the color.
Yeah,
and the flake type of material always have a trouble to print. To my knowledge, we have a project with our customer.
Mm-hmm.
The best one is bismuth oxychloride, which is like 5 microns. Anywhere between is going to be a challenge.
Yep. The downside of that bismuth oxychloride is durability, right? So the durability of the bismuth oxychloride.
But that's give you a printability.
So you get one thing, but but I think in general, I think that's a sort of a market need that's out there is effects that could be jettable. So from a development standpoint, I think your company,
always
mine,
a
and all of
challenge.
us are looking at that.
Even less than 15 micron, it can't, because we did the 9111, which is base material for this. It's not working. You can't print it.
Now, I think you did a good job in the presentation doing some comparisons against aluminum. So this one question may be already covered, but is this product, if this product has 100% radar transparency, how does that compare to the average coatings containing aluminum flake? I think you did show there, obviously, in that benchmark study.
Right, it depends, right? Because the color we picked is 100% aluminum. I think it's like, then the pigmentation is like 27% of aluminum. So it depends on the color.
Okay. But certainly, I think the novelty, you could replace an existing color, but also there's some design attributes that I think are attractive, being on the bluer side for new color development. Next question is, this presentation is focused on the silver gray color. Is research and development also focused on silver gray or for other color base coats as well? Is there any difference of the effect of the pearl pigment to different colors about hiding and flop index? Like, could this be translated into a blue color or red?
Absolutely. Absolutely. In general, our pigment always provide a little better hiding besides the aluminum. So